Today I will explain another recursion tree example. Look at this example. It's t of n equals t of n over 3 plus t of 2n over 3 plus big O of n. First, this recurrence is asymmetric. Given a problem, the subproblem sizes are not equal. One is just 1/3 of its original size, and the other is 2/3 of its original size. So this is a different example. And there is a linear term. And now I show you that its running time is big O of n log n. First, let's guess it by using a recursion tree example. Okay, look at this page a couple of minutes and try to understand what it is. Okay, first, t of n can be represented like this. Okay, then this term further changed into like this. And this further changed into in a similar form. So by doing this repeatedly, we can get this recursion tree. Okay, then now what should we do? Kim Min-seo. Now. Yes, we made this. Okay, then what should we do now? What is remaining? The answer isn't difficult. 이현진. Where we add all the numbers in this tree. Okay? Then it's like this. The sum of the numbers in each level equals Cn. But there is something tricky here. The shape of the tree isn't like this. Do you see the point? So, is it like this? Or like this? Number 1, number 2. Number 1. Number 2. Yes, the answer is number 2. Look at the value here. This is 1/3 of this. So the depth of the leftmost vertex is log n base 3. And how about this? it's log that one. 3 over 2 n. So if we follow the left child, then it becomes 1 faster than when you follow the right child. Okay, then, so up to here, it's Cn in at each level. But if below this level, the sum of each level is less than or equal to Cn. Okay? But we are going to calculate the upper bound of the sum of these numbers. So we use this. Counting more isn't important. But if we count less, so big O notation is to compute the upper bound. So we can count more. We can add more, but we cannot add less. Okay? So Cn times log n base 3 over 2. And look at this. We can change log using base 2. Okay? Then this is constant. So we don't care these two values. So it's big O n log n. Then now we guessed the upper bound is big O of n log n. It remains to prove that it's really big O of n log n by using the substitution method. And this page explains the substitution method. Look at this page and try to understand the proof. More exactly, it's not definition, it's assumption. We assume that this is true when n is n over 3 and 2n over 3. So in the mathematical induction, we assume that this is true for smaller n's. Okay? So by using this, if we replace this by this and this by this, we get this inequality. Okay? And then 방제호. Okay, next. How this expression is explain how this expression is obtained. Okay, by using the property of logarithm, this division is replaced by subtraction, and this multiplication is, where is it? Yes, here. This multiplication between 2/3 and n we can get this. And then add these terms, we get here, and we finally, by doing some calculation, we finally got this. And our aim is T of n is smaller than or equal to this, dn log n. Then from that, we obtained this. How can you obtain this? 유해인, 박영용. Can you explain how this inequality is obtained? What condition or what constraint? Yeah. How can you draw this? By doing what? 김성민.
저 위에 dn 마이너스 로그 3 플러스 3분의 2 거기 플러스 n까지가 0인 부분을 찾아가지고 최선을 만들고
Equals to 0 or less than equal to 0? Or greater than or equal to less than or, okay? So this should be less than or equal to this. Okay, from this condition, this is removed, so this one should be less than or equal to 0. From the inequality, we can get this. And note that D should be alone and all the others should be on the other side. Okay, there are some self-study topics. And now I'll explain some problems in your review. Let me see. In your review 2, number 4, f of x is 4x cubed 2x squared 5x plus 2. And then x is 3. And let's calculate the value of f of x when x is 3. Then let's count the number of multiplications used. Okay, let's try using a simple algorithm. 박종훈. Okay, 박종훈, how many multiplications do you need to calculate this? How many multiplications are required to compute this? 4. 4. Really? 3. Only 3 multiplications. We multiply 4 numbers, but the number of multiplications is 3. So we need 3. And how about this? 박준형, 이승복, 2 and 1. So the total number of multiplications is 6. Can you do better? I can do better. Let me show you. First, change the form of the formula. And then put 3 to x in this way. Then what is the number of multiplications to calculate this? Kimushik. 3, yes. 1, 2, 3. We need 3 multiplications. And compare the number of additions. How many additions in here? 3 additions and 3 additions. So the number of additions doesn't change. Only the number of multiplications are reduced. It is important. We can remove all multiplications if we use more additions. So it is important to maintain the number of additions. 못 알아들은 것 같은데. Okay, that's a joke, so you don't have to understand. And let's think about a general problem. Okay, this is a general polynomial whose degree is n. So let's consider a naive method. Then the number of multiplications. How many multiplications are needed to compute this? N? And how about this? N minus 1 up to 0. So we have to add all these values, then theta of n squared multiplications are needed. Then how about if we write the formula in this way? What is the number of multiplications? Theta of n. Yes. That's a big difference. So this is Arnold's rule. When you evaluate a polynomial, you should evaluate in this way. Polynomials asymptotically. We know that asymptotically n squared is bigger than n, and n cubed is bigger than n squared. And how about n 1.5? It's between these two polynomials asymptotically. Okay, then it's simple up until now. How about this? N log n. It's between n and n squared. Because log n is smaller than n, this is between these two polynomials. Okay, more tricky question is, how about n log n n to the 1.5? Which is bigger? It means it's the same question whether log n and square root n, which is bigger, because we cancellate n from both sides, then we can compare this. Then this is larger in the end. There is an interesting result that if epsilon is bigger than 0, this is true, even though the epsilon is very small, 0.000001, still this is bigger than n log n. Quite strange, but true. And more, how about this? Log n squared. And log n k. Even though k is a million or a billion, this is bigger. Then let's move on to heap sort. We learned sorting algorithms. 전옥은, how many sorting algorithms did you learn? What? In this class. And name one. Name just only one. 조형석. How many sorting algorithms did you learn in this class? Or just name one. 3? Okay, what are they? Merge sort, selection sort, good. Insertion sort, okay, good. So we learned insertion sort and merge sort. 전동엽. Okay, what is the worst case running time of insertion sort? Worst case running time. 최윤주. Worst case running time of insertion sort. 천창근. N squared. Yes, it's n squared. Then Baojun. What is the running time of merge sort? N log n. So merge sort is faster than insertion sort. And log n, n squared. Sometimes insertion sort is faster if the array is already sorted. I showed it. So, but in the worst case, when we compare the worst cases, insertion sort, the merge sort is faster than the insertion sort. 송준호, 이대식. Okay, but when we compare the memory space, which is better? Insertion sort is better. Why? Yes. This is the input array. Insertion sort requires only a couple of new variables. But merge sort requires another array which is the same size of the input array. So insertion sort requires less space. And what do you call a sorting algorithm uses only a small number of additional memory? What do you call it? It's called an in-place sorting algorithm. So insertion sort is more efficient when it comes to the memory space, but merge sort is more efficient when it comes to the running time. Then when you buy something, this one is better in this perspective and this one is better in the other perspective, then you may think, oh, I need the one which only the best things is mixed. Okay? So heap sort is such an example. Its running time is big O of n log n. And it requires only small number of additional variables. So it's an in-place sort. So if you are required to use a sorting algorithm, use heap sort. It may not the best, but it's quite fast. And in the worst case, this is fast, the fastest one. Now first, let me explain the shape of a heap. It's a nearly complete binary tree. A nearly complete binary tree means this. Complete binary tree is defined only 2 to the k minus 1 numbers, such as this is the complete binary tree when we have only one element, only 3 elements, only 7 elements. So if we have only 5 elements, we cannot make a complete binary tree. Okay? But a nearly complete binary tree means we remove the missing numbers from the bottom level and from the right. So if the shape is like this, it's called a nearly complete binary tree. This is an example of a heap with 10 keys in this heap. Okay? This is a shape requirement. Another requirement is the value of keys in the heap. There are 2 kinds of heaps, max heaps and min heaps. Let me explain the max heap first. In the max heap, the key in the parent is greater than or equal to the value in the node. Look at this example. 9, 10 is bigger than 9 and it is bigger than 3. So if 2 keys have the parent-child relationship, the key in the parent is bigger than or equal to the key in the child. So where is the maximum element in the heap? 이성우. 한효경, where is the maximum element in this heap? 윤정희, root? Yes. In the root, there is a maximum element. Okay? Because of the parent-child relationship. And in a subtree like this, the maximum element in the subtree is also in the root of the subtree. That's the heap property. If it is a min heap, the direction of the operator is reversed. The key in the parent is less than or equal to the key in the child. Okay. So, from now on, I'll explain the heap sort using only the max heap. And now I'll explain the implementation of a heap. Even though it looks like a tree, it is stored in the array. Why? You know how to implement a tree, okay? A node is a record or a class or a structure. And in the structure, there are some elements in the structure. The key and pointers to children and a pointer to his parents. Okay? So we need additional pointers. But if we implement the tree, the heap in that way, it cannot be a sorting algorithm. It cannot be an in-place sorting algorithm because of the additional pointers. Additional pointers requires additional memory. So we store the keys in an array. And they are stored in this order: 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. They are stored in level order. And we don't store the edge information. So we don't need any pointers. And the question is, then how can we find children or parent in constant time? It's not difficult. So, assume that a key is stored in the ith element. Then its left child is stored in the 2ith element, and its right child is stored in 2i plus first element. Look at this example. This key is stored in the 3rd element, and its left child is stored 3 times 2 equals 6th element. And this is in the 7th element. So we can find children in constant time by using this calculation. Moreover, we can find the parent in constant time like this. I divided by 2, the floor of this. If I is even like this, its parent is just obtained by just dividing it by 2. But if it is not even, we divide 7 by 2, then we get 3.5, and we take the floor of it, which is 3. So we can get this. Okay. So we can get, I explained the shape of a heap and how the keys in a heap is stored. And finally, how to implement an array to store a heap. Any questions? Okay, then let's wrap up this class now and ask me questions freely in Korean after this class. Okay, then see you next week. And I have an announcement. The programming assignment server is opened again, and the new deadline is tonight. So someone who didn't submit their assignment, do it right now.
Professor, is there new assignments? Or
No new assignments, the old assignments. Okay, then see you next week.